To help us understand how the drywall system is needed to adapt to the tall building, we had to consider the contributing factors for the movement, the scale of their influence, and the displacement effect. The greatest movement influence is meteorological, the effective wind. Its variable strength and direction. Let us take a closer look at the types and effects of this phenomena with a common wind direction. Vortex shedding occurs due to a differential of wind speed or pressure on opposite sides of the structure, with vortexes being formed on the leeward side. Downdrafts are formed when the air movement hits the windward face of the building and is diverted down to street level and the base of the structure. Aerodynamic affects building movement, influences where the force of air pressure is channeled around the architectural features. With these three principal effects combined, it is easy to understand how the building is under constant external wind pressure. Remember that this illustration is demonstrating one wind direction and velocity only. Other air pressure influences which will compound the issue are those neighboring buildings that will contribute leeward vortexes or wind shadow, dependent upon the prevailing wind. In a world where the construction horizon is constantly evolving, new buildings undoubtedly influence the resultant effect on their established neighbors. Let's now take a look at how these wind effects can influence the building's movement within the designed and engineered constraints of the construction. While the following illustrations are accentuated to demonstrate the mechanical movement, building designers will have 3D modeled the construction using finite element analysis software, and these displacements are representative of the permissible engineered profiling. As before, we are demonstrating the resultant movement subject to a fixed wind direction and velocity. However, combining these displacements, and if we also consider the variables associated with the airflow, as already discussed, the construction's movement will be a combination of these with the potential to be influenced by a 360-degree wind effect. In conclusion, the super slim, tall building design has to accommodate only directional movement in response to varying meteorological forces, including the effects of the evolution of the construction landscape. Having considered the structure, we will now need to assess the impact on the internal fit-out and how we respond to the challenge. To simplify our illustration, we will consider the shear building deformer only under the influence of a fixed wind direction and apply the same simulated movement to two perpendicular mounted drywall steel frames installed on the outer perimeter of the top floor. Locking our view relative to the amplified building movement, we can begin to appreciate the displacement relationships. If we then begin to consider the standard fixed constraints at the start to base track junction, then limited freedom of movement can only occur at the unconstrained start to head track interface. Taking a typical floor plate design and an overview of the building's physics, we can see that the further the drywall steel frame is away from the center of building stiffness, the greater the displacement. We can also note that the displacement direction is directly linked to wind direction. Tall building movement at a floor level is therefore only directional and at the whim of the weather, and this is where our challenge begins. The first step was to identify the source of the creaking noise through rudimentary testing. A flexible rig was created into which a 50mm 2-inch steel stud drywall sample construction was built. After multiple sample tests, our findings were not surprising, but the scale of movement versus the audible outcome was. The conclusion was that the drywall test sample fell victim to stiction at the stud head interface, and that the makeup of the wall amplified the sound created. As you will have witnessed, the displacement is nominal, but the impact significant. Finally, the need to address fire performance through a secondary material that would maintain the drywall integrity was identified. An undersized steel insert was developed that could be introduced or encapsulated into the soft body. This insert would follow the profile of the ProStud MotionFrame connector and therefore also latch to the C-stud, but only in a fire scenario. Final prototype testing was concluded and a retrofit scenario fire test executed successfully at UL Laboratories. Clark Dietrich has concluded the preliminary development and testing, and we are now in a position to introduce the product to the market. ProStud MotionFrame connector, an injection molded soft body formed from fire retardant glass, reinforced nylon, 6.60 halogen material, a material widely used in the construction industry within electrical installations, with an encapsulated steel insert for fire performance. Simple installation of the component into the stud twist locks and is retained within the C-head track. Freedom of movement and deflection, even at complex junctions where the impacted drywall design is affected by opposing directional movement. The ProStud MotionFrame connector will allow drywall systems that close the gap on tall buildings. Development going forward will mitigate noise generation in tall buildings through the elimination of stiction at the stud head and will deliver the performance requirements of a traditional drywall construction.